First student to comment on the total number of items that just dropped from the ceiling gets a gold star and a shout out on Schoology, maybe, if you're first. So not only do you have to, I guess, be first to watch the video, but I tried to be tricky with my falling object game. Hey, welcome to the first review lecture, the first of 3, where we're going to be going back over all of the different units of the school year. I'm going to try to hit the highlights in the largest chunks I can in regards to the topics that I think they'll most likely ask questions about. Of course, while you're preparing for the AP exam, you'll absolutely want to just use your notes. All right, I taught you everything that was fair game. So going over all of the examples will be useful. The other thing that you'll find is the Schoology practice, which most of those assignments are about 40 questions because I'm covering multiple units in these lectures, that they'll do a pretty good job at not only addressing stuff that I cover in this video, but those in-between concepts and maybe the more detailed questions in regards to stuff that I don't write on these whiteboards in a moment. So anyway, my hope is that with your notes, this video and the series of 3 review videos and Schoology, that you will have seen everything again, and you'll be ready for your AP exam. So let's see how it goes. You should already have your slides written. You'll notice we had a huge upgrade in Rooster because this is special. This is a big deal. We've changed gears now. It's where we get to see stuff again. So let's just knock these slides off together. So when we started our foundations, which was basically the review of pre-AP, we started off with a few things. If you look over your notes, you'll be able to go over the way to separate compounds. We went over things like filtering, distillation, chromatography. And if you remember, we compared the pros and cons of each of them, or not always pros and cons, but some of them were really good at separating heterogeneous mixtures, while some were better at homogeneous mixtures. And there's an absolute chance that one of your FRQs will have that as one of the smaller questions in regards to which tool, what would be the best process by separating it. A certain mixture, and you'll want to be able to not only pick one, but of course defend your choice. So on the slide, I summarized them a little bit. Filtering separates mixtures based on differences in size particle. That would be like the filter paper pouring something that's got objects dissolved in it or just objects floating in it and pouring it through filter paper. Water goes through, the objects don't. And then it goes over distillation and chromatography as well. So make sure you have those notes handy. So law of conservation of mass, of course, is the reason that we balance equations. So be prepared for somewhere in that in your FRQ section. I'm going to be saying FRQ a lot. I'm planning on using these videos for future school years. So of course, it all applies to multiple choice also. But this year is COVID-19 and we're only doing FRQs. But beware of the unbalanced equation. All right, just make sure those coefficients are correct so that we can serve all mass. Significant figures. So make sure you're good at your sig fig rules. I know that a lot of y'all, when you come into tutoring, the only reason you're missing questions sometimes is because of sig figs. It's not a make or break. All right, if you do all the work right and your sig fig is wrong, it's not like you missed the whole problem. All right, there's partial credit everywhere that there can be partial credit, and usually the multiple choice questions don't even look at sig figs. It's just those FRQs that you can really lose points for them. But one of the things to remember is when we're using measuring devices in lab, that you always estimate 1 digit more than what the instrument is capable of measuring. So if you're using a ruler that goes to the 10th place, all right, it's just got, it's got the whole number and then it's got 10 little marks before you get to the next whole number. All right, well, that's measuring to the 10th place, but that means you get to estimate to the 100th place. 1 digit more than what the device is capable of measuring. And you've seen the test. You ran into, I think it was a Barrett question that we did on one of my tests, where it said, what would the student record as the volume? inside this burette. You had to know which direction to go on the burette. Some of y'all weren't good at that during titration, but you needed to estimate an additional sig fig. An FRQ that I did pull from the past that you might remember that we did earlier this school year had to do with which of the following pieces of glassware would be the best to measure, this X amount of volume. And one of the things that was a big deal for you to answer that question was knowing that a volumetric flask, while it's super precise, can only measure a singular quantity. So if remember, those volumetric flasks have one graduation. So if that's ever an option, you have to make sure that, like if it says you need 250 mils of your volume and you're going to use a volumetric flask, well, then you have to be using a 250 mil volumetric flask because it's got that one graduation on it. But if you look at your slide, you'll see that it's, besides the burette, it's the most precise, but it's got a singular graduation, and never use a beaker for measuring volume. Limiting reactants for stoichiometry. So I highly anticipate a stoichiometric angle on one of your FRQs. So just make sure that you're ready for the different ways it can look at it. All right, it probably won't be straight stoichiometry. A lot of times limiting reactant is going to be a larger part of it, so that you need to know which of the reactants was used up first and therefore stopped the reaction. Percent yield is another very common stoichiometric twist. Remember, with a percent yield, it's going to be comparing a theoretical yield and an actual yield together. The theoretical yield is what your math on paper gives you when we do our dimensional analysis, whereas an actual yield is where the student goes to the lab, does the lab, and gets a number. Those two numbers are going to be different. The actual yield is going to be hopefully just slightly less than the theoretical yield that you got on paper. And then by dividing actual over theoretical times 100, it would give you that percentage. And then gas stoichiometry is the other common twist, which we just finished in our last unit. So hopefully you're good at that. The other big thing from unit 1 that I wanted to go back over was these particulate drawings, just because there is there's a likelihood that you'll have to draw one. I mean, maybe you'll just have to analyze one, but I want you to be able to draw it. So you'll need to be able to remember how to differentiate between. So I guess I'll just, I would like for you to look at these and guess what's what. Remember, things that you can look at while looking at a particulate is going to be states of matter. So that's going to be solid, liquid, gas. And then if you decide it's pure, then it could be an element or a compound. If you decide it's impure, then it can be homogeneous or heterogeneous. So there's quite a bit of information on each of them that you can give. So I'll just go through these real quick, and hopefully you remember this as being easy. I would say that A is a pure gas, only one type of particle there, and it's showing that it's gaseous. B is a heterogeneous mixture, a mixture because you can see clearly there's two different substances mixed together in there. Heterogeneous because they've allowed us the ability to draw an imaginary line and separate them. Remember, the heterogeneous are the easier to separate because you can usually easily see the parts of the mixture. C I would label as a homogeneous mixture. Again, we clearly have two different types of substances in C, but I cannot easily draw an imaginary line to separate them, showing us that it's homogeneous. D I would call a liquid compound. It's pure because you'll see that all of the parts are identical to each other, but I know it's a liquid because there is some disorganization there. If it was a solid, the particles would have been in a more predictable pattern. E I would call a solid compound, most likely water actually, based on the way that compound looks like it's set up. But when you compare D to E, you can see that there is a very obvious difference in the organization of those. E is more organized to show us it's solid. I would say that F is a solid element, not a compound this time. We have nothing bonded to anything, but it's still in that solid format. G, I would say, I could take G a step further and probably call it a diatomic element in the gaseous form. Diatomic, most likely because it's, it's bonded to its twin, it looks like there, and then hopefully the gaseous is obvious to you. And then finally, H, I would call a gaseous element, only one type of particle there. And again, it's not lined up along the bottom at all. It's floating around. So make sure you have those ideas kind of handy in your brain. You're dismissed. Just kidding, you're not dismissed. We have to keep going. Okay, so let's move into Unit 2. So as we started talking about reactions, we had to look at we had to revisit stuff like net ionic equations, solubility chart, and then we kind of tiptoed around neutralization and stuff like that. So some stuff we needed to absolutely know about the ability to dissolve. You've got your strong electrolytes will 100% dissociate. All right, so knowing strong versus weak was really important. And then it listed on that slide says the strong electrolytes are your soluble salts, strong acids, strong bases will completely dissociate. Your weak electrolytes don't completely dissociate. And one of the ways that we would show that is using an equilibrium arrow in our reactions. And that included slightly soluble salts, weak acids, and weak bases. So how do we know strong acid versus strong base? Some of y'all were haunted by this throughout the unit, and it's got to be in your brain, or for this year, I guess, written down beside you at home. But if you remember, for the binary acids, we would say I bring clay. So that was HI, HBr, and HCl are automatically strong. So we just had that memorized. And then for the other acids, the way that we found if they were strong or not is if they contained 2 or more oxygens when compared to hydrogen. All right. Also remember that there is a default element that automatically makes an acid weak, which was carbon. I left that off the slide, I'm sorry. So remember, a carbon containing acid is automatically weak. So add that to your notes if you don't have it. For the bases, just looking at your hydroxides, if you have your hydroxide bonded to any alkali metal, automatically strong. Then there were the 3 alkaline earth metals that trickled into the strong zone, and they're listed there for you. Ooh, I put Br for bromine. That's a typo. It should be Ba. Hey, look at your slides. It says, your slides say bromine, calcium, strontium. That's supposed to be barium, calcium, strontium. It was my evil twin. I'm sorry. So based off these different ideas of what completely dissociates a singular arrow and what will dissociate at equilibrium, we could be given a compound and asked to write a dissociation equation. And yay, I get to write on my whiteboards now. So if you look at the slide, it says write the dissociation equation for acetic acid. So write acetic acid before I do. All right, so we just want to show how he's going to dissociate. So there's my acetic acid. Does everybody agree with what I've written so far? Now, if you just shouted no at your computer, you probably shook your screen because you got so angry. You would say, well, that's not the proper type of yield sign to use for the dissociation of acetic acid because, hey, look, carbon. It's a carbon-containing acid. It's not going to 100% dissociate since it's weak. So I need this to be an equilibrium arrow to show that we know it's weak. When it dissociates, though, it will turn into its part here. Unintended sound effect, I promise. But anyway, so here are your 2 products after the dissociation takes place. One of the things that we covered that I didn't put into the slides was the dissociation of polyprotic acids. Remember that they dissociate stepwise, meaning that if this was a polyprotic acid, something like sulfuric acid, that this would be 2 steps long. You would have one H dissociate, and then it would leave you with, remember, sulfuric acid is H2SO4. After step 1, it would be HSO4 minus, since it's lost one of those. One of his protons, and then it would dissociate again to lose that second hydrogen. So it's those polyprotics that dissociate in multiple steps. All right, so other general solubility rules. Now, if you remember things like Argentina and Sri Lanka, then that's really important. So make sure that you look back over the mnemonics that I taught you in order to have them memorized. But what I just showed you on that slide is the super simplification of your solubility rules. Really looking over past AP exams, it's probably all you would really need to know on the test in terms of the way they ask, but it says that alkali metal salts, all right, so your group 1 metals that are ionically bonded, your ammonium salts, NH4, bonded to an anion, and then all nitrates are absolutely always soluble. And if you're going to go in only knowing one thing about your solubility rules, know that those 3 things are always soluble. The other thing the slide mentions is the definition of a net ionic equation. If you remember a lot of you can write net ionic equations without writing complete ionic equations first. We're going to do a full example right here because why not? We're all bored at home. But remember the parts of the complete ionic equation that don't make it into the net ionic equation because they duplicate themselves as reactants and products are called spectator ions. These are the guys that are actually not participating in any part of the reaction that we care about. So the slide says, write the net ionic equation when sodium hydroxide is mixed with phosphoric acid. I'm going to absolutely run out of space here doing this, so we'll have to bear with each other. So let's see if this is madness. All right, so sodium hydroxide, right, with phosphoric acid. So we've got sodium hydroxide reacting with phosphoric acid. All right, and what that's going to produce, well, this is a double replacement. All right, so it looks like it's going to produce sodium phosphate. That's a P. All right, and then water. All right, so taking a look at my setup here, all right, it looks like we're going to have these as being aqueous. I probably could have changed colors. Hey, look, it's an alkali metal salt, so we know that he's definitely soluble. All right, and then what do we label water as? If it's just pure water, what state of matter is he going to be in? All right, well, that's liquid. That's going to be important as we're writing our complete ionic equation. So let's do complete ionic first. I'll try to color code because this is where I know I won't have enough space. So if you remember, we're going to be dissociate. Oh, you know what? We're not balanced. It's going to be a 3:1 to 1 to 3 mole ratio, and that's going to be important. Can you see that 3? What's the screen look like? Yeah, you can see it. All right. So if you remember, the coefficients will absolutely be necessary because we need to account. We need to account for how many of each item there is. Hey, I'm going to lower this window. I think we're starting to glare out. Okay, I look cool. So anyways, let's go ahead and break this guy apart. So my sodium hydroxide here is a strong base. So he's going to end up being 3 Na pluses, all right, because you notice that coefficient is coming into play there. And then that's going to be 3 plus 3 OH minuses, because of course in my complete ionic, I'm basically separating everything that needs to be separated. Now, you'll notice that my next species is a weak acid though. How do I know that the phosphoric acid is weak? Well, look at the ratio of hydrogens to oxygens. there's only a one atom difference, and the only way for it to be strong is if there's at least 2 more oxygens than there are hydrogens. So what am I going to do? I'm going to not dissociate them. All right. He gets to stay together there. All right. As we move to the other side, all right, we've got my soluble salt over here. So he's going to break apart into 3 Na pluses. All right. Notice how the subscript becomes a coefficient while we're writing this, just to show the number of them that there are. All right. And then we have just the one phosphate ion there. And then, hey, look, the liquid state. We don't dissociate the liquid state while we're doing this. So this is going to be added to 3 waters. Actually did pretty good as far as the lines go. Now, the only stuff that we cross out, the only stuff that becomes spectators is going to be the items that are the exact same on both sides of the equation. So, man, this is a bad time of day suddenly. Let me see if I can make it clip up. You want to come say hi to the students? Tell them Happy Easter. Their Easter was yesterday. I mean, not them to you, you to them.
Happy Easter.
Show them what you're eating.
No.
Well, it wasn't carrot, Reese's Pieces. Oh, y'all are both eating them? Okay. All right. Well, tell them that joke I told you yesterday.
What'd you say?
I don't know. Oh, here, you want to show them the plants that the Easter Bunny did? You want to? Show them at home. Is that it? You have anything to say? You're just gonna make them want you to eat candy? Okay. Oh, it's spilling. Sorry. Hey, look, I fixed the light. I'm brilliant. Okay. The only spectator ions that I see here appear to be the sodiums. These 3 Na pluses. All right. Nothing else matches each other verbatim. So when I'm gonna write the complete ionic equation, I'm sorry, the net ionic equation, I'll bring down all of the other stuff. So the final will be these 3 OH minuses plus the H3 PO4 is going to yield the PO4 minus 3 and the water. And in green there, you can now see the net ionic equation. Aqueous, aqueous, aqueous liquid. So hopefully you remember all of that fun stuff. All right, well, let's change gears and let's think about kinetics. The good thing about us revisiting kinetics is that if you remember the integrated rate law, I made a part of our solids and liquids unit, and we had to revisit some of our rate laws ideas somewhat recently. So that's good news. All right, so let's move into kinetics. Okay, so kinetics is going to look at the way and the rate at which the reactions happen, how fast they take place. If you remember, in order for a reaction to take place, we had to reach the activation energy. It was easiest to reach the activation energy when particles were not only colliding more and more often, but they have to collide at the correct orientation. So that first little note I put on there kind of summarized a whole big idea in regards to making reactions take place. And the words that are in there, including things like activation energy and particle collision and breaking of bonds, is really good FRQ verbiage to have in your mind if you are having to look at the rate of reaction. So no matter what angle they're asking you about kinetics, I hope that you'll throw in the idea of activation energy. Okay, so looking back at the slide, remember that when writing rate laws, that coefficients of the reactants will become exponents in the rate law. So you can see on that slide, it says K equals concentration of A squared times the concentration of B, which of course, if you look at the reaction that's going off of, the reactant A had a coefficient of 2. So remember, that was one of our basic ways of writing rate laws. Again, very good verbiage as a way to be wordy on your FRQ and show them what you know are those ways to speed up a reaction. Okay, so adding a catalyst, you even remember it from biology, was a way to lower the activation energy. All right, you have to have a certain amount of energy to get the reaction to start, and if you make that value be less, it's easier for it to start. Increase in the reactants can increase collisions. All right, so if you have a higher amount of those initial reactants, there's a higher probability that they will run into each other in the correct orientation and more often, which will make the reaction go faster. Increased surface area will help speed up a reaction again that just can increase the rate of collisions. And then pressure and temperature. So I don't anticipate it asking you 5 ways to list it, but if it does give you a scenario and you can pinpoint 1 or 2 or a few of those ways to speed up a reaction, you'll definitely want to mention them. The next asterisk there is going to actually refer back to the integrated rate law. If you remember, that's where we studied half-lives. Can you get me some water? Some water. If you remember, everything has a half-life. It doesn't matter what type of order reaction it is, but all first-order reactions are going to be radioactive. And it's those radioactives that have a constant half-life no matter what the initial concentration is. That's really important to know because that half-life equation that's on your sheet that we use, remember the divided by 0.693, that's on your sheet, but that only works for first-order reactions because nowhere in that equation is the concentration of the reactants even mentioned, because it doesn't matter. The half-life is the same no matter how much you have. So there's a chance that knowing that fact is going to be important. And then, as we'll see in a second, don't forget that when you're given a mechanism or when you're asked about the kinetics of a reaction, the only thing that determines the kinetics is the slowest step, the rate determining step. We're all only as fast as, if you're running a relay and there's 4 of us and one of us is terrible, all right, and never ran in our life, then the rate at which we finish that 4-person lap is going to depend solely on the slowest person. So the slowest step in the reaction is what will overall determine the rate. This lecture is brought to you by Sam's Purified Water. It's got hydrogen and oxygen in it. Boom. Okay, so let's take a look then at an example of a way to analyze one of these kinetics. Okay, I tried to get smart here because I didn't want you to have to watch me write all that, rather. So here's the mechanism that it gave us. It's a 3-step mechanism. You'll see in red, it's got the slow, fast, fast in regards to the rate of the steps. There was several things it can ask you here. Like if it wants you to do an energy profile, I would know that the energy profile would overall have 3 humps. And I know that the humps would basically look like this based off of this order of steps. The taller hump, of course, representing the slow step. So this would be the RDS here. But there are 2 other steps. If you remember, there was items in the reaction during the mechanisms, these broken down parts of the reaction that can end up at the end of steps, all right? And that had to do with the vocab of intermediates and catalysts. So intermediates and catalysts can exist at the end of steps, and we will revisit what's what as we analyze this problem. So one of the things that we are asked to do sometimes is come up with a overall reaction based on looking at the mechanism. The way that we're able to determine that is by looking at each step of the mechanism, and anywhere one of the reactants completely matches one of the products, they're going to ultimately cancel each other out. So as you compare and look over these, I can find a couple things that match that. All right, for example, my HOI looks exactly like an HOI in those two spots. Hey, look, my I minuses look exactly the same in those two spots. However, I don't get to cross them out because they're both on the reactant side. Remember, it's got to be a reactant that matches a product verbatim. The only other things that actually match each other perfectly here are going to be the OH minuses, because what I see here is that I have an OH minus there and an OH minus there, which is exactly two OH minuses. Check it out. Two OH minuses. So with that said, I can now compile all of the stuff that didn't cancel out, and we can get an overall reaction. So what I'm going to do is I'll take my hydrogen peroxide here. All right, it looks like we're going to have two I minuses. All right, you'll notice that I'm combining them to make it pretty. All right, and then we also have two H pluses. Moving over to the product side, it looks like we have an I2. And the only other thing are these two waters. And now I have an overall reaction that I was able to deduce from the mechanism. All right. And now there's some other stuff though that we could be asked. For example, we could be asked about intermediates and we could be asked about catalysts. Now, intermediates are the names of the items that are used up at the end of steps. These are where intermediates can exist, and this is where catalysts can exist. Catalysts are items that are used up in the very, very last step of the reaction. So as I look over here and try to figure out if I had any intermediates, I'll see that, yes, I did have intermediates, all right? We had HOI was an intermediate, all right? We had OH minus was an intermediate. We had OH minus was again an intermediate. And again, these are items that were crossed out as a product of one of the mechanisms. So we had three intermediates, it looks like there. Did we have any catalysts? Well, no, we didn't. There was no catalyst here because look, the catalyst can only exist if something was eliminated as a product in the last step of the mechanism. All right, well then what would the rate law be? How would we actually write the rate law? Well, check it out. We've got my equation up here. Now for the rate law, it's the rate determining step though, the slow step, that's going to determine the way that it's written. So that's going to be this guy here. All right. So as I take a look at the way that the slow step is written, I would say K equals, because that's how my rate law looks. All right. I'll take my H2O2. All right. I'm going to take my I minus. And these are both going to be first order. All right. Remember, we can find out the order of each reactant by looking at its exponent. There's no coefficient here, so it's going to automatically be a 1. And then, but here's the other thing that can be tricky about writing the rate law. I mean, that looks like it. We looked at the slow step, we looked at these reactants, and we wrote the rate law. Anybody remember what else would be in this rate law? Any item, any reactant in the overall reaction that is not a part of the slow step should still be in the rate law, but identified as a zero order reactant. Because remember, a zero order reactant is one that isn't altering the rate in any way whatsoever. That's why the zero is there. So I would also therefore add this H plus and call him zero order, just to show that he's not a part of the RDS. All right, so there's a whole bunch of stuff that we were able to come up with, intermediates, catalysts, profile, overall reaction, rate law, just by being given a mechanism. So there's a variety of questions that they could ask. The last topic we're going to cover in this first super review is our general equilibrium. So if you remember when we're looking at general equilibrium, it's another K equals expression. And it's where we take all of the products raised to the power of their coefficients divided by all of the reactants raised to the power of their coefficients. Now, this is where the quadratic formula and stuff like that came into play, depending on what they were wanting us to solve for, because we were using Rice tables and stuff. So you got to be looking for that and make sure you remember how to solve quadratics on your calculator using the solver. Some other things to remember: only aqueous and gaseous can appear in equilibrium expressions. So sometimes you have like a solid show up, especially if we're doing something like KSP, where the solid shows up and it just gets a big X beneath itself in the Rice table, because the only things that can go into equilibrium are going to be AQ and G. So watch out for your states of matter. The larger the value of K, the more product there is at equilibrium. So it's just some other general stuff to keep in mind. Now, one of the things that we talked about after we wrote equilibrium expressions was, okay, well, what about when equilibrium is thrown off? The reaction's going to try to fix itself. And who gave us the ways that it fixes itself? That was Le Chatelier. So let me go ahead and write this equation up here while we talk about it so I can reference it. Let's get rid of this. Turn one sideways. All right, so this equation on your slide, it looks like it's endothermic because heat is being put in. So it's saying heat is being put into a system of dinitrogen tetraoxide. All right, and then that is producing 2 nitrogen dioxides. All right, now it gave us the states of matter here, and it let us know that these guys were both gaseous, so that's important. And then what we can do with this using Le Chatelier is we can say, okay, well, what if we altered some stuff? All right, what if we change some things about the environment this reaction's happening in? Which direction would the reaction have to shift in order to go back into equilibrium if it was messing up whoa, the rates being equal? So let's go ahead and take a look at what might happen. So here's my first question. What if we increased the heat? All right, what if we made there be more heat? Which direction would it shift? Well, here's the way you thought about it. All right, if you increase, in this case, since it's endothermic, heat's considered a reactant. If you made there be more heat on this side than there was supposed to be, well, it wants to get rid of that. So what's it going to do? It's going to shift the other direction to make that extra heat go away. So I would say increasing the heat would make it be a right shift. All right, so that'll be true for endothermic. All right, what if we increased the NO2? What if we made there be more nitrogen dioxide? All right, well, now suddenly it's at equilibrium now, but if you make there be more product, it's going to say, okay, well, we don't want more product, so let's shift back towards the reactants to get rid of that extra nitrogen dioxide that's existing there. That would be a left shift. All right, and then there's the one that you had to think about a little bit more. What if we increased the volume of the container that the reaction's happening in? All right, well, this made us think about Boyle's law, because increasing the volume directly, well, rather inversely, is going to affect the pressure, because if volume goes up, that means that pressure goes down, in which case this system is going to want to fix that lower pressure by shifting towards the side with more pressure. All right, so how do we know which side has more pressure? Well, we go off the number of moles of gas that you can find on each side. How many moles of gas are there over here on the left? 1. How many moles of gas are there over here on the right? 2. So if the pressure has gone down, but I want the pressure then to go back up, we want to shift towards the side with more moles. In this case, it's a right shift. So there's a quick Le Chatelier review. Schoology will give you some more. Hey, we're almost done. 42 minutes. I'm tired of talking. All right. Last slide. I absolutely anticipate a rice table question to be asked. We want to make sure, all right, that slide reminds you what the phrase rice, not ice, rice, talks about, or what each part of the acronym means. So you'll definitely want that. The problem, though, that I give us at the bottom for us to practice is actually a problem that involves Q. If you remember, some of our basic rice table problems have the assumption that it's going to shift one direction or the other. The way that you know which direction it shifts is it's always going to shift towards the zeros. So if you were given a certain amount of reactant and you know it was going to be a forward reaction, then that's where you would put, okay, well, minus X on this side and plus X on this side. Q was our fake K that we would use whenever we weren't sure of the shift. We were given a reaction and there was amounts of everything. There was initial concentrations of everything. So we didn't know for sure if it was going to shift right or left, and we could do a Q to K comparison to figure out if it would be in forward or reverse. So what you'll notice at the bottom of the slide is it gives us a reaction. Let's go ahead and write that down, of chlorine reacting with fluorine. So it's going to give us Cl2 reacting with F2. All right, and it looks like that is producing 2 ClF. All right, everything here is gaseous, which is important. All right. And then it does give us a K value. So I keep squinting. Kc of 19.9. All right, that's all given information that we have for the problem. And now it wants to know a direction shift based on given amounts, or rather given concentrations of everything. So if we were going to do a rice table for this, and we have to use a Q because, again, it gives us amounts of everything instead of something being at 0. So I don't know which direction it's going to shift. Well, my rice table is going to have, well, there's the R because that's the reaction. So here's I, C, and E. All right. So my I is going to be my initial concentrations. So it looks like we're at 0.4 molar here. So this is going to be 0.4 for the chlorine. It gives us 0.2 for the fluorine. And then it gives us 7.3 for the chlorine monofluoride. All right, so there's all the initial concentrations. However, it's going to end up giving us, okay, so, sorry. We've got these numbers here and we know, okay, well, in order to find my equilibrium, we take the concentration of the reactant, the concentration of the products over the concentration of the reactants. And what we have here is, well, values for everything. So we're able to do that. So I'm going to start with my products on top. Let me change colors. Where we're going to have 7.3 squared. All right, why squared? Well, remember, whenever we're writing our equilibrium expressions, the coefficients become subscripts, so or superscripts. So we're going to have that over, and now it's going to be the products of these bottom guys. So it's ultimately going to be 0.4 times 0.2. Now, neither of them are raised to a power because, well, they don't have coefficients. So if we run this expression, this is going to give us Q, because by running these opening numbers of all the initial concentrations, because there are no zeros, that's where my Q value will come from. And it looks like we're going to get a Q value of roughly 670. Well, look at these two numbers, all right? If you look at the question, all right, it's actually asking what direction is it going to shift? Is it going to shift to the left or is it going to shift to the right? Well, by comparing K to Q, I can make the assumption, and what I see here is that Q is greater than K, obviously. And if you look in your notes, you'll see that anytime Q is greater than K, it's going to be a left shift. That was a terrible arrow, I'm sorry. All right, so what does that even mean? Well, it means that on the change, if it was wanting us to go further and solve the problem and not just ask us for the direction shift, all right, I would say, all right, well, then I'm going to be going plus X here, and minus 2X here, because if you remember, the coefficients do show up in that C line, all right? But I'm going to be adding towards the reactants because we're shifting that direction and subtracting the products because we're taking from that direction. Now, when these problems aren't Q problems, when this, like for example, that we're done with the problem, but so don't let this twist your mind. But if this 7.3 was a 0 initially, we wouldn't have needed to find Q. Instead, we would have known that it's going to shift towards the 0 because that would be automatic, in which case this would have been minus X plus 2X. And then to find E, of course, that's where you put these all together. This would be 0.4 plus X, 0.2 plus X. If I go back to my 7.3, it's 7.3 minus 2X. And there could be some plugging and chugging going on in regards to working it out. If you compare this overview to your notes from each of the units, you'll see that hopefully you have a good refresher to go with all those other examples we did in class. So you've got a rich amount of resources available to you. So be using them as you get all of these things back in your brain. And good luck on the assignments as you head back and remember them as well.